Hey everyone, GM, good night, good morning, wherever you are in the world. Welcome to one of our awesome workshop sessions for our Block Magic Hackathon. Definitely drop in the chat where you're watching us from. It's always so nice to see where everyone is plugging in from. And right now we'll have an amazing session with Kevin Nielsen from Moonbeam. He will take us through how to build better dApps with Moonbeam Precompiles. And yeah, buckle up, have some fun. That's what we want. And with that, Kevin, I'll hand it over to you.
Thank you so much, Sophia. Hello, everyone, and welcome back. Moonbeam is extremely glad to be sponsoring the Block Magic Hackathon. We participated in events with Chainlink in the past, and they're always the best hackathons and in-person events. So we're thrilled to be a part of it. And yeah, today is going to be a little bit of a very focused look at the bounties that we have. So this is very relevant. This is very topical. And hopefully it'll give you some ideas for what you can build with our bounties. And if you already have an idea in mind, then this will just show you, some of the ways that you can use these precompiles. So Moonbeam, I'll start sharing a quick little slideshow, but this is going to be hands-on. We're going to have some demo components. So let me share this. Cool. So I can see, I'm assuming everybody can see as well, but maybe if anyone wants to drop in the chat, that would be awesome. Cool. So Moonbeam, as you guys know, is a parachain on Polkadot. We are Ethereum compatible, and it's not a compromise. Moonbeam is 100% seamless and Ethereum compatible. So this means you can take any dApp from one that you deploy on Ethereum or any other smart contract chain, and you can deploy it on Moonbeam without making any changes. And this also works for when you're querying the Moonbeam JSON RPC. You can make the same request that you'd make to an Ethereum node. You can make that to a Moonbeam node without making any changes. So everything is very seamless, but we didn't just stop there and say, okay, here, we're going to take this EVM and we're going to put it on Polkadot and we're going to call it a day. We've gone way beyond that. And one of the ways that we do that is with these precompiles. So Moonbeam is built on top of Substrate, and Substrate is the building block layer of Polkadot parachains. So when you're launching a blockchain on Polkadot, and parachain is just a fancy name for a blockchain on Polkadot, when you're launching and building your parachain, you can pick and choose different building blocks for your chain. You can say things like, I'd like the governance module. You can say, I'd like the cross-chain transfers module. You can say, I would like to include a staking module. And you can take bits and pieces that are already open source, or you can create your own from scratch, or you can take one that's already out there and you can say, this is pretty close to what we want, but we're just going to tailor it to our needs. And something that's unique is that Moonbeam is accessible through both the Ethereum API and the Substrate API. So the Substrate API, also known as the Polkadot API, you can submit transactions, you can submit calls to different palettes and modules. But something to understand is that a lot of these powerful features, such as staking and governance and cross-chain transfers, these are native to the Polkadot side of Moonbeam, to this Substrate side. And so if you're not used to interacting with the Polkadot API, some of these features could be a little bit trickier for you. And so that's why we built precompiles, so that you can access these features from the Ethereum API. In fact, you can access them directly from either a smart contract in Solidity, so from your own smart contract, or you can access them simply through a web dApp. You can just have a dApp and you can call these precompiles. You don't necessarily have to call them through a smart contract. You can just make a call to it directly as you would with any other smart contract, which is really cool. So we've got actually dozens of these precompiles, and they all touch a different piece of these powerful features that Moonbeam offers through Polkadot. And so that includes things like staking, that includes governance, cross-chain transfers, and many more. But the ones that we have highlighted here for the hackathon are ones that can really help you build out better user experiences. And that's really what we're most excited about at the end of the day, is that you want to build better dApps for your users. You want to make people happy, and you want to give them a much better experience than maybe they're used to. And so I'll just want to walk you through a little bit of some of the technicalities of Moonbeam Precompiles, what you need to know and what you don't need to know. So you do not need to know Rust. You don't need to know Substrate. You don't have to understand really anything about Polkadot. And that's something that's quite powerful. So Polkadot can be tricky. And there's lots of terminology and things like that. But you don't actually need to know all of that in order to interact with Moonbeam's precompiles. All you need to know is what precompile are you looking for. So if you're saying, hey, I want to do some staking related features, well, you're going to look for the staking precompile. And then you can go ahead and look that up in Moonbeam's docs. And we've got extensive documentation for every single precompile that we offer. So if you're looking for the staking one, you'd head to staking functions. You'll see the address for the precompile. This is probably the most important thing that you need to know. And then, of course, you want to know all the different methods that you can interact with. And if you prefer to jump straight to the interface, you can do that as well. And you can find that at stakinginterface.sol. And another thing to point out is that we always label our interface here with the address of the precompile. So you don't need to jump between the docs and the interface. Instead, you can always find it here, either as a constant or as a comment. We typically have both on our precompiles. And just to kind of reiterate how precompiles work, these Solidity interfaces behave just like regular smart contracts and regular smart contract interfaces. Now, under the hood, when you call a precompile, it's actually kind of a shortcut into, it doesn't exactly go through the EVM because these are Polkadot native functions. So it's kind of like short circuiting. It's kind of a shortcut that goes into the runtime and says, hey, I see you want to interact with the staking palette. And so this Ethereum interface is just a way for you to interact with it from the Ethereum side, but it's really going over into the Polkadot or Substrate side of the runtime. And so, all you really need to know is what functionality are you looking for? What is the precompile address? They are all different for each one. So if we go to X tokens, for example, this will have a different address. Now, typically, we make sure that the addresses are the same across all of our networks. So Moonbase Alpha is the test network. Moonriver is the canary network. It is a production network, but it's more experimental. And then Moonbeam is the mainnet. When you are launching your projects for the Chainlink Block Magic Hackathon, you'll be deploying either to Moonbase Alpha or to Moonbeam. Okay, so we talked about you need to know which precompile you're looking for. You need to know where to find it. And of course, you need to know what function to call and what parameters you want to provide to that. And you can find those all in the documentation. So what can you use these precompiles for? So we mentioned that they're a very easy way to access these powerful Substrate features through the Ethereum side. But they also allow you to improve the user experience for your users. And one of the ways you can do that is through the batch precompile. And Polkadot has a number of batching functionalities. You can access these again through the Polkadot side, or you can access them here with the batch precompile. And we have a number of different ways, 3 to be exact, that you can group transactions together in a smart manner. So it's not just willy-nilly, like let's try to execute everything and see what happens, but rather you can choose some logic as to how you'd like your transactions executed. Would you like to have all of them being executed all together, as in everything succeeds or everything fails? Would you like to try to execute everything? And if some fail, you can just ignore those and keep going. That's what batch sum is. batch sum will try to execute every single call that you provide to it. If one fails, it's fine. If multiple ones fail, that's also fine. It will keep going and it'll try to execute all the calls that you have provided to it. So this is the simplest method of the batch precompile in terms of you're not having any logic here as to how you'd like them grouped. You just like to try to execute everything and hopefully it works and goes through. Now, each method of the batch precompile uses the exact same parameters. So these parameters that you see here on the right, you have an address array of 2 addresses. You have an array of values. So values, just the amount of native token that you'd like to send along with the call. It could be 0. You also have an array of the call data, and you also have an array for the gas limit. Gas limit, this is an optional parameter here. So the idea here is that if you want to segment off your calls, if you want to restrict them to use a certain amount of gas, you can provide that here. You can also just leave it as an empty array, and it will execute as normal by estimating gas and using as much as it needs to get the call done. Gonzalo has a great question here. Can we use the precompile to save gas? Yes, you absolutely can. So if you're executing, let's say, for example, you're minting a bunch of NFTs, right? If you try to say the call mint NFT 1, and then you do another call for mint NFT 2, not using the batch precompile. If you add up those two, that's going to use more gas than if you do these 2 minting ones right within the batch precompile. So it does end up saving some gas. It isn't, it can't, change physics in terms of how, how gas works and things like that. So you're not going to witness unexpectedly large dramatic changes here, but it does benefit you for sure because overhead from the call can be combined, and you can save some gas by batching these together. But I would say simplicity is a major key as well. And another benefit is you can group transactions logically. So the second method is you can batch everything until one fails. And if one fails, you can stop. And in this case, batch until failure. Anything that succeeded before the failure call is not reverted. So that first call, let's say you have 3 calls, right? And I'm going to go through actually in the later slides. I have a couple examples. So I'll show those so that it makes a little bit more sense than just talking about it. But the third one that we have is batch all. And so this is all or nothing. Everything needs to succeed or everything will fail. And so if one call fails, then the entire thing fails. It doesn't matter that the first call was successful. Everything just fails altogether. So yeah, I wanted to provide these specific examples because I think it clears things up a little bit. So let's say here with batch sum, right? We have 3 different calls that we're trying to execute. The first one is successful. The second one is a failure. And the third one here is successful as well. That would equate to being a batch transaction success. So the batch transaction would go through, even though we had one call that was a failure. It's not a problem. It shows as completed on a block explorer and everything looks good. For batch sum until failure, this would be an instance, suppose we have the first contract call is a success. The second one is a failure. The third one is not attempted. So we don't know whether the third one was going to be successful or not. We don't even try to execute it. We got to the second one, it failed. And so we're not even going to try going to the third one. But the first one was successful, and this is not reverted. So the first one worked. We're just going to leave it as is. We're not going to revert it or call it a failure. So that batch transaction would go through as a success on a blockchain explorer, and everything would look good there. So lastly, we have this batch all logic, and this is all or nothing. Everything needs to succeed or everything will fail. And the example here is we have a success call 1, we have a failure call 2, and at this point, everything stops and the entire transaction is reverted. So even though the first one was successful, that does not go through. It was reverted because the later ones did not succeed. So this entire batch transaction would revert. And the idea here is, let's say you're doing an approval and a swap on a DEX, and both are 2 independent transactions. So you need to approve an ERC20 token first, and then you'll go ahead and make your swap. Now, a lot of blockchains at one point in time were doing unlimited token approvals, right? And this is a bit dangerous because if there was some sort of smart contract hack or an attack, by granting an unlimited token approval, you are at risk. And so it's safer to only grant an approval for the amount of tokens that you want to swap. And sure, this costs a little bit more gas, but another hurdle is that users have to click and confirm 2 transactions every time. So a lot of times people approve the unlimited token allowance because they didn't want to have to approve 2 transactions each time. Well, something you can do with the batch all method here is you can take the approval and you can take the swap transaction and you can batch them together in a batch all call to combine both of these in a manner which makes perfect sense. So when I say perfect sense, I mean you only want to have the approval call go through if you know that the swap is going to succeed. And likewise, you only want to attempt to try the swap if you know that the approval already went through. So in this case, batch all would be perfect because you couple the approval to the swap. And so neither is going to execute without the other one succeeding. This is good for safety. This is good for convenience. And it's just a better user experience. Nobody wants to have to click approve and then wait 30 seconds and then go ahead and click confirm again. They want to do it all at once. And that's something that the batch precompile can give you. So Gonzalo said, can precompile transactions save gas? The idea would be to generate a package of several transactions and send them all together. Yes, absolutely, Gonzalo. Combining these together can save gas, as opposed to doing independent transactions one by one. You're not going to see, dramatic gas savings, but you will see savings because there is overhead with each transaction. And when you combine those into the batch one, you do save. Yeah, absolutely. It does make a difference. So I did want to quickly go through, what are the parameters? Each batch method takes the same parameters, so they don't change for any of them, regardless of whether you do batch all, batch sum, or batch sum until failure. They're all the same, so that is quite cool. And additionally, they also emit the same events. So you'll see a subcall succeeded event, and you'll also see a subcall failed event. And this can be helpful for keeping track. You don't have to pay attention to these if you don't need them. But our first parameter is an address array of 2 addresses. So most likely you're going to be interacting with a contract. So these are going to be an array of contract addresses. Otherwise, let's say, for example, you're just sending out funds. You can just put an end user account address here as well. If you are dispersing, let's say you have a faucet or something like that, and you're dispersing native token, you can absolutely group addresses together. And then in the value, you could put in the amount of value that you're sending along. This is of the native token. So the native token is dev for Moonbase Alpha, and it's called Glimmer for Moonbeam. If you're just doing a contract interaction here, you can leave this empty. And when you leave it empty, you just have an open close array in terms of formatting. Okay, and then we have call data. These are going to be the call data that we're sending along to each contract to each contract call that we're making. So this will include the selector for the function, and it'll include the parameter data that you're including for each one. So if the contract call doesn't have any parameters, if you're just calling a method, it doesn't take any parameters, then it'll just be the function selector. And lastly, this was the gas limit that I was talking about. You don't have to specify a gas limit. You can leave it as open bracket and close bracket. That's totally fine. If you leave it empty, it will just use the typical gas estimation mechanics, and it will use exactly as much as it needs. But the gas limit is useful for if you want to segment off. If you want to say, hey, I think this call might use a little bit more gas. I want to either stop it from using too much gas, or perhaps you want to allocate a lot. So let's do a quick demo of batch.sol and see how it works in a hands-on way. So the first thing I'll do is I will head to the docs site, because I want to kind of take you through what you would do, as a typical user. So I'm going to head to the batch page, and we'll pay attention to the address here. This is important. But the first thing we want to do is we want to open up batch.sol. There you can see the full interface here. And let's copy this into Remix. So we'll call it batch.sol. I'm going to go ahead and compile it. And I'm going to copy this address here. And we're going to go to deploy and run. And something that's very important is make sure that you are connected to the right network. By default, you'll probably go to Remix VM, but that's not going to include any of the Moonbeam precompiles there in Remix VM. So if you are trying this out and you notice that you're getting like null responses for each one, or you're getting success but no response, that's typically indicative that you are on the Remix VM and not on the Moonbase Alpha network. So make sure you're on the right one. 1287 is the chain ID for. Oh, sorry about that. Let me do this here. I will zoom in quite a lot. Thank you for bringing that up. How's that? Is that better, guys? Let me know if I need to zoom in any further. So a precompile is already deployed. We're not deploying the precompile. Instead, we're just accessing it here. So we're going to access it at the address, which is here. And we'll press @address. And I think I already had a couple left over here. So let's just start fresh and press @address. And we can expand and we can see all the methods here. So for example, we can start with the batch all. And just for demonstration purposes, I have a simple smart contract that we can use that's called incrementer.sol. And it's a very simple contract here on Moonbase Alpha. All it does is have one simple function, which allows you to increment a counter that's stored in the contract. So right now the number is 278. And what we'll be doing is we'll be using the batch precompile to make various different calls, or the same call to this contract multiple times. So here in Remix, I need to start filling out the parameters. So 2 is going to be the smart contract address. So let's copy this. And one important thing to keep in mind is that the way that the batch precompile can keep track of the different subcalls that you want to make is simply by the amount of values in the array. So if you have 3 different calls, you're going to have 3 different 2 values in the array. This includes even if they are all the same contract address. You can't provide just one. They all need to be matched. So if we're going to make 2 calls, for example, we're going to paste in the contract address 2 times. And that'll be the same for the other fields as well. In the case of value, we don't want to provide any native token with our call, so we can just leave that as an empty array. In terms of call data, we're going to get that from the increment side here. We can see that it's visible right here, but it's just a bit easier to copy from MetaMask. So all I'm doing is copying the hex data here, which you can also get right there. But for some reason, you can't copy it right there. So that's why I'm getting it from MetaMask. So let's do the same thing. We're going to have an open bracket and an open quotes, as well as a closed quotes, comma, open quotes, closed quotes, closed brackets. Now I'm voicing out each one of these notations here because it is very picky. So if you're trying around, if you don't include quotes, you'll have a problem. If you don't include a comma, you'll have a problem. If you forget a bracket here and there, you'll get an issue. And sometimes this can be frustrating to debug, right? So what I recommend is if you're going to batch together many different calls, get 1 or 2 calls working together, and then you'll have the formatting down correctly, and that'll make it much easier than trying to debug something where you've got 10 or 20 calls. So simplify it down, try it with just 1 or 2 calls, get that working, and then you'll get to the next one. This isn't hard by any means. It's just sometimes it can be tricky trying to figure out, if you leave out a quote here or there and trying to figure out where your error is. So with the gas limit, we're going to leave that as an empty array here. We don't need to provide any gas limit. So as a demonstration to show you that this works, I said that the number here was 278. So we can refresh that, and we'll come back here in 30 seconds or so after this transaction goes through. So it's asking me to confirm the transaction. And I don't think you can see MetaMask. Yeah, you can't see MetaMask. That's okay. All I'm doing is confirming the batch all transaction. In the meantime, Gonzalo says, what would happen if I were to generate different purchase and sale transactions of different ERC20 tokens? Could I precompile all of those transactions? Gonzalo, meaning could you batch them all into one transaction? Yes, absolutely, you can. So just like we're doing here, you would have the to contract address. So this would probably be the sale contract address, I'm guessing, or it depends on how the NFT contract is set up. If you're minting, for example, that would be directly to the NFT contract. If it's a posted on a sale website, then the NFT might be stored within a different contract. So you would make the call to that contract, and then you would make the buy call data here. The buy call data maybe takes a price, or maybe it takes some other parameters, like a to address where you want the NFT sent. You would provide all that, and you would be able to batch those transactions together. And you could think about whether you want to do, batch some, batch all, or batch some until failure. So let's take another look. Our transaction went through. And let's take a look at the number. And it did indeed increment up to 280. So this is because we included 2 calls to this contract from the batch precompile. So I know this is a very simple example, and we could do something way more complicated, but I just wanted to show you in this example how this works. And we are also going to demonstrate the call permit precompile in a couple minutes as well. And we'll also be using the incrementer contract for this to do a very similar interaction, but just using call permit. So let's see. I think I've covered everything that I'd like to talk about the batch precompile. Anybody have any more questions on the batch? Sure. So typically, it depends, right? If you're doing like a swap, let's say for a swap on a DEX, right? Pricing is constantly changing, right? That might not be the best use for the batch precompile. You can certainly get the call data, but if you want to make like repetitive transactions where the pricing is constantly changing, that might be a tough thing to automate for sure. But if you're just doing something like, let's say, minting, for example, minting, you're always going to have like similar call data. Pricing is not going to change in that case. Yeah. it would just be things where I was thinking, if you're like rebalancing or doing something like that, where you need to constantly get, updated call data, that could be, slightly trickier. Okay, so in terms of the next precompile that we have, this would be, we call it the call permit precompile. And call permit is just a fancy way for you to do a gasless transaction, or a fancy name for a gasless transaction. And call permit speaks to more of the interaction, meaning a user will permit you to dispatch a transaction on their behalf. And in doing so, they have a gasless transaction because they only need to sign a transaction. They don't need to confirm a transaction. They don't need to spend any gas. All they're doing is signing an intent. And then it is up to the dApp to actually go out and dispatch that. So what is a gasless transaction? A gasless transaction is where a user will sign an intent of something they would like to do. And this is a very tightly controlled signature. So this signature authorizes a particular transaction, and it's limited in the sense that this cannot be resent. So if, for example, let's say I authorize sending 1 ETH to Bobby, it's going to have a nonce, and it's also going to have a deadline attached to it. So Bobby can't just say, oh, this is nice. Kevin signed a message for me to receive 1 ETH. Let me send that to the network. He'll go ahead, he'll get his 1 ETH. But then if Bobby says, you know what, I really like that 1 ETH, I'd like to do that a couple more times. If he tries to submit that transaction again, it will fail because the signature is no longer valid. The signature was valid just for that one transaction with that nonce and with those exact transaction details. So if Bobby receives the 1 ETH, he tries to submit the transaction again, the nonce will have changed. And in this case, with call permit, there is a global nonce that increments for each transaction submitted through the call permit precompile. So it's actually different from the nonce that would appear in your wallet, but the concept is the same. So you could have an account that has 1,000 transactions, and it could be the first time it's interacting with the call permit precompile. In this case, the global nonce here would be 1. And I'll actually show you there is a method that you can look up and see what that nonce is using the call permit precompile. Oh, yes, absolutely. Absolutely. So David is asking, what are other benefits of batching apart from gas optimization and automation? So gas optimization, sure, that's one thing, right? I would say, yeah, that's a benefit. It's certainly a benefit. I think the biggest benefit really is, providing benefits to your users, right? You can make it so that they don't need to approve many different transactions at once. You can make it so they can do an approval and a swap together. Let's say somebody's purchasing, 3 NFTs. You could have them go select the boxes like 1, 2, 3, and then confirm a checkout. So they don't need to go click buy, click buy, click buy. Instead, it's just check, 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 and then buy all at once. And so that could be cool, and that could be a nicer experience. Another example, claiming staking rewards and things like that. If you're doing like a DeFi application and a user is in many different farms, for example, each farm might have its own, claim rewards button, and the user might have to go, 1, 2, 3, 4, go down through all these different farms. That could take a lot of time, and it could be kind of annoying because even though transactions are fast, you're still going to be waiting, 10 seconds or so for each one to wait for it to go through. So if you can batch those together, you can provide, an experience to your users that is that's simplified and much more enjoyable. Yeah, absolutely. Yeah, I'm sure there's other examples. I was just thinking of like the farming one and things like that, where users are doing something that's repetitive, right? They may be wanting to claim their farming rewards, twice a day, 3 times a day, something like that. And so when you think about all that time really adds up, and you can really improve a user experience that way. So going back to the call permit precompile, this is a way for users to authorize a transaction. And again, yep, as Gonzalo says, this is security focused. So a user is going to sign a message, and then the dApp, so that could be you as the dApp builder, you can choose to submit that. And the way that you choose to submit that is you take the signature and you submit it through the call permit precompile. So when you submit it through the call permit precompile, you are paying for the gas associated with that transaction. It's typically not a lot, but you are paying for that. And this is something that can benefit users in a number of different ways, right? So one example, of course, is somebody doesn't have any gas. Maybe they just bridged over to Moonbeam and they have, let's say, USDC, or let's say they have Ethereum, right? Now they've got wrapped Ethereum on Moonbeam. For them to go out and get Moonbeam tokens, they might have to go to an exchange. They might have to go and the other option is to do a gasless transaction. So if they bridge over USDC, they've got funds. And for example, there is a DEX called StelSwap, BeamSwap. These DEXs have gasless swap and enabled. And I have a little demo that I'll do in just a second to show how that works. So when you are submitting this call permit that you've got, this message that you've got from the user and this signature, the call permit precompile is going to check all the details of the transaction. They're going to check the deadline. And the deadline is a timestamp in Unix seconds, which I want to show you what that looks like. You probably all know, but the deadline looks like this. And it is a number of seconds since January 1, 1970. This is standard across all of computer science. It's not just something that's specific to Web3. But this deadline is important because depending on the design of your application, you might want to have a limit. If you want to authorize somebody, to pay a bill or something like that, then maybe you only want that authorization to last for a day, an hour, a month, whatever it is. So for the purposes of our demonstration, we're going to be, getting a timestamp that's way off in the future because we don't really care what the deadline is. So the precompile is going to check all that. If everything looks good, if everything is correct, if the nonce is fine, the signature, all that, then of course the transaction will be dispatched, and it'll look just like a normal transaction to the rest of the network. So what I mean by that is, the dApp that you're interacting with, right? Let's say that you're purchasing an NFT, right? Or you're playing a game, and maybe there's a check-in in the game that you need to do. The contract that you're interacting with does not care that this was a gasless transaction. So there's no changes that you need to make to the receiving dApp. All of that stays the same. To the receiving dApp, it does not care that it was a gasless transaction. It can't tell the difference. Like, everything is the same. And so this is a big deal that you don't need to change any smart contract logic with whatever you're interacting with. So the only thing that you would change with call permit is you would change the prompt on your website. So if you have a dApp, rather than having a user confirm a transaction, instead you're going to prompt them to sign a message. And you'll also include the logic, presumably, to submit that to the call permit precompile. Now, another thing to think of is that you don't have to, for instance, be the person to submit that in this case. For the hackathon, you certainly will be. But for a production dApp, for example, you might outsource this to somebody like Bioconomy or another team, maybe Open Zeppelin, where they just do this all day, right? And they can also do more advanced things, like they can check for stuck transactions. They can increase, gas prices automatically. They can do all things like that, which are perhaps, more robust for a production setting. For this hackathon, of course, you do not need to do anything of that. You'll just be submitting it to the Call Permit Precompile, which we will demonstrate exactly how to do that. So yeah, this is basically what I just talked about, which is that the dApp here, the app that you're interacting with, you don't need to change anything about the smart contract that gets called. And the only thing that you're going to be changing is what is presented to the user. So rather than presenting them with a transaction to confirm, you're going to be presenting them with a message to sign. And then you're going to take that and submit it to the Call Permit Precompile. So what exactly does the Call Permit Precompile look like, and what are we actually signing here, right? So when you present to the user a message to sign, there are going to be a couple different values, and that's going to include, I've talked about the deadline, I've talked about the contract address, the call data, also the nonce. And so all this information is very, very important, and we'll see exactly how this works in just a second. And so once we go to actually dispatch the transaction, when you, as the dApp developer, when you say, hey, I've got the signature, I need to go ahead and submit this to the network, how do I do that? So that's where you interact with the Call Permit Precompile, and you'll be asked to provide a couple different things. You'll be asked for the from address, so this is who signed the message. You'll be asked for the to address, so this is the contract that you're interacting with, the value. You'll be asked for the call data. You'll be asked for a gas limit, as well as a deadline. And these are signature values here, the V, R, and S values. So this gets generated after the user signs the message. So you'll need to take all of this and you'll submit it to the Call Permit Precompile, and then the transaction will go through, and that's it. So I want to show a quick demo of what this looks like, and we'll start preparing a gasless transaction here, and we'll submit that through the Call Permit Precompile. So there's a site here called callpermit-demo.netlify.app. And we can go ahead and connect our MetaMask to the site. And we're asked for a contract address and all those parameters that I was talking about before. So let's set up a gasless call to actually interact with our incrementer contract. So we said before the number was at 280. It should still be there. But let's go ahead and set up a gasless call to this contract. So our to address is going to be the contract address. Oops. Value, we don't need to include anything here. So we can leave that empty, or we can put 0. For call data, we're going to be using the same call data that we did before. And we can get that over here from the right tab. And I'm just connecting this so that I can more easily copy it. I'm not actually confirming this right transaction here. I'm just copying the transaction data. Okay, and gas limit, we can leave that empty. We don't actually need that. Okay, for deadline, we do need the deadline. So let's go ahead and copy. I'm copying this. It's from like a year in the future. You can just take the current timestamp, and then you can add a digit or change a digit. What you just want to make sure is if you choose the current time, that's not going to work, because if you choose the current time, by the time you actually submit it, it won't be valid. So make sure that you're not choosing the current time. Oops, I put this in the wrong field. There we go. We want it in the deadline field. And then we're going to press sign data. And I'm prompted right now in MetaMask to sign a message. And I see all the data. I see the from, the to, the value, the data, the nonce, the gas limit, all that stuff. So I'm pressing sign. And I see there was a quick little error here. So let me just refresh that page. You see how we got this gas limit here? So I originally pasted the time into this gas limit field, and it feels like it was the page was sticky, and so it saved that value. So let's just refresh. Let's paste in the contract address. Please, can you send the call permit demo website and the Unix epic timestamp? Yeah, absolutely. I'm going to share this with Sophia, and then because I'm not in the public chat at the moment, but I think Sophia will be able to share this with the rest of the group. Okay, thank you so much. Okay, so we're filling out the contract address. For value, we can leave this empty. For data, we're copying the same value, which I also have here from when we were interacting with the batch precompile. So we'll put that in the data field. And for deadline, I'm going to take the time that is a year in the future. And I'm just going to clean this up. So I'm going to press sign. I'm going to confirm the signature in MetaMask. And here we can see everything looks good. So I've got the from, the to, I've got the value here of 0. I've got the data. The gas limit here is 0. It's not actually a gas limit of 0. It's just kind of like a placeholder here. We're not limiting the gas for this. Okay, for deadline, we've got that. And then we've got the VR and S values. So the VR and S values are part of our signature. And so we are going to take all this information and we're going to submit it through the Call Permit Precompile. So let's do what we always do, which is go to the Moonbeam docs site. Let's go to Call Permit. And let's open up callpermit.sol. So if I open this up, I'm going to copy and paste the contents of this into Remix. So we'll create a new file. We'll call it callpermit.sol. And let's go ahead and compile it. We'll head to deploy and run. And remember to get the call permit address up top. And if I expand this, we'll see we have a couple different methods. So dispatch is what we're going to be doing, but I also wanted to show you the nonces tab. So if we look to see my address here was this. If you want to see how many transactions I've done through call permit, we can see I've done 7. And so this nonce is 7. And this doesn't show up here in the demo dApp because the dApp is automatically going to calculate that nonce value for you. So when I went ahead and signed the message, it presented me a nonce value of 7. And so this is something that you would want to check. Excuse me. So let's go ahead and dispatch our transaction. So I'm going to bounce between these two pages here. But you can see all the values, so I'm just copying and pasting them in. We got our from, we got our to, we've got a value of 0, we've got a data of this, we've got a gas limit of 0, we've got a deadline. Again, 0 is not a gas limit of 0, it's just no limit. Deadline, we're going to copy that in. Now, it is very important that all these values match. So what I mean is, if you think, oh, my deadline is this, I'm just going to put in like a random number that's really big. That random number that's really big has to be the same one that you signed in call permit. Because if it's any different, it's not going to be valid. And you see the V, R, and S values of the signature. These happen to be in order, V, R, and S as well. But in some applications, they might be presented differently, right? So just make sure that you're copying them into the right fields. If you don't, this is a great way for the there to be an error. So you just want to make sure that you're copying everything exactly as you see. And that's it. We'll press transact. Let's see. It says it's using too much gas. Let's try that again. Let's see what we messed up here. I see. I think it's because I chose the gas limit of 0. So let's actually, instead of specifying a gas limit of 0, let's specify a gas limit of 1 million, which is going to be way too high, but that's fine. So value is 0, data. We said we had that before. So let's copy that. Gas limit, let's specify 1 million. I think that's 1 million. Yeah. And deadline, we're going to use the same one from here. And I'll press sign. And I'm going to sign it in MetaMask. Okay. So I've got the signature. The difference now is that the gas limit is 1 million rather than 0. So sorry about that. Let's go ahead and submit all this information. Most of the stuff can actually stay the same, except for gas limit is going to be 1 million. And the signature values are going to change. So we need to copy those as well. All right, let's try this now. Cool. So MetaMask is popping up. I'm going to confirm the transaction. And I know you can't see MetaMask right now, but I'm submitting this from a different account. Actually, you can see that account here in the upper left-hand corner. You can see that this account that ends in E35 is different from the account in my call permit one. The from account here begins in 0x6 CAF, which is different from here. So all I'm doing is I'm submitting this from another account to show you that we're not just doing a normal transaction, but another account is dispatching this call permit transaction. So me as the dApp developer here could be submitting this transaction on behalf of the user. So I'm confirming the transaction now. And while that's going through, let's just take a look at the rest of the slides. So I will show a real life example of this swap for gas feature. This will be on Stel Swap or Beam Swap. Yeah, let's go ahead and give that a shot. So let's say I just bridged over to Moonbeam, right? And let's say that I don't have the exact, I don't have any Glimmer, for example. But I do have, let's say I have USDC or Ethereum or any of these supported tokens. Typically it is a limited subset here because you are going to have to pay a fee, right? The fee is typically a little bit larger than it would be for a normal swap. So you typically, here in this case, it's 2.5%. In this case, you only want to do the gasless swap, if you really need to, but it is extremely convenient, especially for people who are bridging over. But this is a production example of the call permit dApp in use. So you're going to be signing a message, and in return, you're going to be making a swap. And so Stel Swap is dispatching this swap on your behalf, and you're also authorizing, a transfer of fees. So they're going to give you, as part of this message that you're signing, you're going to be giving them a little bit in fees. So let's head back to Remix. We'll see that our transaction went through. And to double check it, let's head over to Incrementer. Let's head over to Read. Let's refresh the page. And if everything worked, it should go up to 281, which it did. So that was an example here of using the Call Permit Precompile to dispatch a transaction in a gasless manner. So I know this was like a simple example, but I wanted to focus the example here to be on Call Permit itself and not a complex smart contract interaction. Obviously, when you're making a gasless transaction, right, you might be doing a swap, you might be doing purchasing of an NFT, you might be doing anything like that. But it's really the same thing that we just demonstrated. Your call data is going to change. Your call data might be longer. Your to contract address is going to change, but everything else really is going to stay the same. And the other thing to point out about the gas limit here, I originally put in like a placeholder value of 0. That was the wrong answer. Instead, the right answer is just put in a realistic gas limit or put in something that's large. So Moonbeam has a block gas limit of something like 15 million, a per transaction limit of something around 12 million. And so you can just put in a value. 1 million is way more than enough for any regular transaction. So you can just put that in. And again, just make sure that whatever you sign, so if you sign 1 million, make sure that you put in here in the dispatch field also 1 million. And this is because the call permit precompile is going to check and make sure that the gas limit here that you provided matches the one that was in the signature. So for security purposes and safety purposes, if you in the dispatch, if you say, no, actually the gas limit was actually 12 million, then it's going to change the values that would be required in the signature. And so the call permit won't work. You need to make sure that those values match exactly. Cool. So as we're coming to the end, I just wanted to give folks, another chance to ask questions. And of course, I'll go over the bounties that we have. You may have already seen them, but I'll do a quick recap of them. So this right here is just an example of Stell swap, where we're doing this swap for gas. And it's an example of what you're signing within MetaMask. So in MetaMask, you can see the value, the deadline, the nonce, who you're interacting with, and all that. We've already done this. We've already interacted with the call permit demo dApp, so we can breeze right through here. And lastly, I just wanted to talk about the bounties. So we've got 2 bounties with 2 prizes each. So you've got 4 prizes in total. The first one is focused on a gasless transaction experience. So integrate call permit into an existing dApp or build a dApp that uses it. And our bounties are designed to be, very stackable. So they're designed to be easy enough that you can integrate this into a dApp that you're already building. You don't need to design your entire dApp around this bounty. It's something that you can go for, 5 bounties and check them all off, and you can add Moonbeam to that list. So we've got a $3,000 first place prize and a $750 second place prize, which is the same prize structure for using batch.sol. So the second bounty, use batch.sol to batch transactions together. And this can be an existing dApp or your dApp that you're already working on. It's designed to be easy to integrate, right? Use it to improve the user experience. Use it in a way that makes sense, right? Meaning pick out one that's appropriate, right? Pick out batch all or batch sum until failure. Pick out an appropriate method. And maybe you can, include in the README, here's why I batched it this way or something like that. And again, all this at the end of the day is meant to improve the user experience. Moonbeam is focused on, providing better user experiences, both cross-chain and both, locally to Moonbeam itself. But we want to make, Web3 easier for everybody to use and interact with. And we're excited to have you, join us on this mission. So that's all I have for today. And feel free to check out our Moonbeam docs site. That's probably the most important resource that you have for the hackathon. So it's just docs.moonbeam.network. And if you want to see information about the precompiles, you can head over here to development interfaces. We also have tutorials where we go into more depth. So if we head over to here and we head over to interact with precompiles, we take you beyond the basics here. So we're not going to be doing like a simple incrementer contract, but instead here we're doing a prove and swap. And this is a bit longer of a tutorial, but it really goes into depth on everything that you need to know. Same thing for call permit here on sending gasless transactions. We go really in depth here, and we also show you exactly what you need to do. So this is good probably for a bit more advanced. You first want to check the precompile section, and then you can come over here to the tutorials one, and this can help you go further. Oh, thank you, Sergio. Pleasure having you here.
Awesome. Thank you so much, Kevin. If you want, feel free to share with me the link you're sharing, and I'll drop it in the chat so everyone can bookmark it.
Oh, thank you so much, Sophia. Oh, yeah, sorry. Let me send that. Okay, private chat. Got it.
Awesome. Okay, I'm going to drop it in the chat for all of you to save it, use it, and reuse it as much as you want for this hackathon. Again, if you want to have a full overview on the Moonbeam challenges, bounties, and requirements, do go to our hackathon dev post page. I just dropped the link in the chat. So chainlinkblockmagic.devpost.com. You have there the full description for requirements. And again, Kevin, thank you so much for this useful presentation. Let us know if you still have any questions. Just drop them in the chat as last chance to make your questions while we still have Kevin. I will give you 1 minute to see if any question drops, and if not, we'll close it out. Okay. Seems we're good. Everyone is good, and that's always great. So again, thanks everyone for tuning in to spend some time with us. Keep hacking, keep building with Moonbeam. We're definitely looking forward to see everyone's projects. We're super excited. And we will still have one more workshop today from Dabble Club, so stay tuned. And again, tomorrow. And yeah, Kevin, thank you so much again. And thank you, everyone. And oh, I do like that comment. 100% easier than the Microsoft Hackathon with AI. Awesome. That's what we like to hear. But yeah, thank you so much, everyone. Have a great day, great evening, and we'll see you in the next workshop. Bye, everyone.
Good luck, everyone. Thanks so much for joining. Thanks, Sophia.